Welcome to Understand the Math. In this Calculus 1 video, we're learning how derivatives determine the shape of a graph. We'll start with the increasing-decreasing test to identify where a function is increasing or decreasing, and then use the first derivative test to find local maximum and minimum values. Next, we'll explore concavity and how inflection points are related to the second derivative. And then finally, we'll apply the second derivative test to determine where a critical number corresponds to a local maximum or minimum value. Be sure to download the free guided notes to follow along and work through the examples with me. Let's now learn about the increasing-decreasing test and walk through some examples. The increasing-decreasing test is used to find where a function is increasing or decreasing. In this graph, we have the function y is equal to f of x, and we're going to look at where it is increasing and decreasing. If f prime of x is greater than 0, our function has a positive slope and it is increasing. If f prime of x is less than 0, such as on the left-hand side of our graph, the function has a negative slope and it is decreasing. Let's now walk through some examples. In this first set of examples, we are going to find the intervals on which f of x is increasing or decreasing. Just to make things easier, I've written down 3 steps that we can follow. We're first going to find the critical numbers, and then we're going to find the value of f prime to the left and right of each of those critical numbers. And then step 3, we can just write down the intervals for increasing, that is when f prime is greater than 0, or decreasing when f prime is less than 0. Let's look at our first example. We're given the function f of x is equal to 3x to the 4th minus 4x cubed minus 12x squared plus 5. The first thing that we're going to do is find the critical numbers, so we're going to start by taking the derivative. F prime of x is equal to 12x cubed minus 12x squared minus 24x. To find the critical numbers, we set that equal to 0. It looks like we can factor out a 12x, and then we're left with x squared minus x minus 2. We can then factor our quadratic. Let's see, we can factor it as x plus 1, and then x minus 2. And then we set all 3 of those terms equal to 0, and we get x is equal to 0, minus 1, and 2. Our second step is to find the values of f prime to the left and right of these 3 numbers. I'm going to highlight f prime because that is what we're going to have to be looking at. Let's now make a number line. This is going to be x, and we're going to put our critical points on it. We have -1, we have 0, and then we have 2. The spacing doesn't matter at all. We're now going to be looking at the value of f prime to the left and right of these 3 points. When you're working with a polynomial, the region to the left and the region to the right of all the critical points is determined by the leading term of f prime. The leading term has an x cubed in it, so it is going to be negative when x is negative, and it's going to be positive when x is positive. That just makes it a little bit easier. Now what we have to do is look at values between -1 and 0, and then between 0 and 2. For this part, I think it's easiest if we look at the factored form of f prime, which is this part right here. Over here on the right, I am going to make a table. I'm going to put down x, And then I'm going to put all of the factors that I highlighted in orange. So we have x, x plus 1, and x minus 2. And we are going to be looking to see if those factors are positive or negative. The point that I'm going to choose between -1 and 0 is -1/2. And then -1/2 is negative. -1/2 plus 1 is positive. And then -1/2 minus 2 is negative. Now let's pick a point between 0 and 2. I think the easiest point is 1. So 1 is positive, 1 plus 1 is positive, and then 1 minus 2 is negative. In the region between -1 and 0, we have a negative times a positive times a negative, so that's going to give us a positive. And then in the region between 0 and 2, we have a positive, positive, and a negative, so that is going to be negative. I think before we go to step 3 and write down the intervals for increasing or decreasing, I've always found that it helps to draw an increasing or a decreasing line in each interval. So in our leftmost interval, we have decreasing, then we have increasing, decreasing, and increasing. Now we can just write down the intervals for increasing and decreasing. Our function is decreasing on the interval from -infinity to -1 and on the interval from 0 to 2. And then our function is increasing on the interval from -1 to 0, and then our rightmost interval from 2 to infinity. And we'll go ahead and we'll highlight those answers. Before we go on to the next problem, let's look up here on the right at our graph. Our critical points are the points right here, here, and here. They're the points where our function changes from increasing to decreasing or vice versa. And you can see on the graph that our function is decreasing in this interval and in this interval, and then it's increasing in this interval and in that interval, just like we calculated. Now let's look at our second example. We're given the function f of x is equal to 2 plus the quantity x minus 5 cubed. Just like we did with our first example, we are going to start by taking the derivative. We have f prime at x is equal to 3 times x minus 5 squared, and then the derivative of what's inside is just 1. And we set that equal to 0, and we get a value x is equal to 5. For step 2, we are going to draw our number line. And this time we only have one point to put on it, and that is that x is equal to 5. Now we need to find the value of f prime to the left and right of 5. Let's go ahead and highlight this because that's what we have to look at. Notice that that is a function that is squared, so it is always positive. So we're going to have a positive value for f prime to the left and a positive value to the right. So our function is increasing and increasing. One thing we have to keep in mind though, at 5, the derivative is equal to 0, so the function has a horizontal tangent and is not increasing there. So for our answer for part 3, we have to say that our function is increasing on -infinity to 5 and from 5 to infinity. And we have to leave out the 0.5. Here's our answer then. And before we go on to the next problem, let's look at our graph over here on the right. This is our critical point when x is equal to 5. You can see that there is a horizontal tangent there. And then to the left and right of that point, our function is increasing. In this next example, we are given a graph of y is equal to the derivative of f. And we want to find on what intervals is f of x increasing or decreasing. Since this is a graph of f prime, we can see where the critical values are. They're going to be at 1, at 3, and at 6, because that's where our derivative is equal to 0. Now we need to find the value of f prime to the left and right of these critical points. Let's go ahead and let's make a graph here, and let's put x on it. And then let's go ahead and put our points. We have 1, we have 3, and we have 6. And we are looking at the value of f prime. To the left of 1, f prime is positive. Between 1 and 3, f prime is negative because it lies below the x-axis. And then you can see the pattern. Between 3 and 6, it lies above the x-axis, so it is positive. And then for points greater than 6, it is negative. So we can see that our function is going to be increasing, then decreasing, then increasing, then decreasing. We can then say that our function is increasing on the intervals from -infinity to 1 and 3 to 6. And it is going to be decreasing on the intervals from 1 to 3 and 6 to infinity. And those are our answers. We're now going to learn about the first derivative test and walk through some examples. The first derivative test is used to find where a function has a local maximum or a local minimum. The first derivative test tells us that if f prime changes from positive to negative at a point C, you can see this down here in our graph. We have a point C, and our derivative is positive and then negative, which means that our graph is increasing and then decreasing, and that means that we're going to have a local max at x is equal to c. In a similar way, if f prime changes from negative to positive at a point C, here's C, and f prime is negative and then positive, so our function is decreasing and then increasing, and that means that we have a local min at x is equal to c. I always think that it helps to draw those lines because you can see easily that you have a max or a min. Let's now walk through some examples. We are going to use the first derivative test to find the local maximum and minimum values of f of x. Just to make things easier, I have written down some steps that we can follow. The first step is to find the critical numbers. The second step is to find the value of f prime to the left and right of each critical number. And then our third step is to just calculate the local maximum. That is going to be where f prime changes from positive to negative. And then find the local minimum. And that is where f prime changes from negative to positive. In our first example, we're given the function f of x is equal to x cubed minus 6x squared plus 5. For our first step, we are going to find the critical values. So we're going to start by taking the derivative. F prime at x is 3x squared minus 12x, and then we set that equal to 0. We can factor out a 3x, so we're left with x minus 4. And this gives us that x is equal to 0 and x is equal to 4. Those are our critical values. In our second step, we are going to take these critical values and we are going to put them on our number line. The nice thing is that spacing doesn't matter. So here's 0 and here is 4. And we are going to be looking at the value of f prime. Let me go ahead and highlight f prime so we can see what to look back at. Because f prime is a polynomial, when we look at the regions to the left and right of our critical numbers, we only have to look at our leading term, which is x squared. That term is positive, so we know that to the left and right, f prime is going to be positive, and then all we have to do is now just pick a point in the middle. I'm going to choose x is equal to 1, and we're going to have to see what f prime is. F prime at 1 is just going to be 3 minus 12, and that is negative. So we're going to put a negative here. And then let's go ahead and let's draw some lines. When f prime is positive, our function is increasing, then it's decreasing, and then it is increasing. Now let's look at our third step. We just have to find the value of the local maximum and local minimum. We are going to have a local maximum at 0. So let's calculate f at 0. Let me highlight this because this is what we're looking back up at to find f of 0. So f of 0 is just 5. Now let's calculate f at 4. That's where our local minimum is going to be. And this is 4 cubed minus 6 times 4 squared, which is 16, plus 5. And that is, let's see, 4 cubed is 64, minus 96 plus 5, and that adds up to be minus 27. So for our answer, we can say that 5 is our local max, and minus 27 is our local min. Before we go on to our next example, let's take a quick look at our graph. Our critical values are here and here. That's where our function changes from increasing to decreasing, as well as where our local max and mins are. And you can see that right here, at x is equal to 0, we have a local max. And when x is equal to 4, we have a local min. In our second example, we are given the function f of x is equal to x plus 2 sine x, and we're also given that x is in the interval from 0 to 2 pi. I always like to do a trigonometry example because I think students always find these challenging. Our first step is to go ahead and take the derivative. We have f prime of x is equal to 1 plus 2 cosine x, and now we're going to set that equal to 0. So we get cosine x is equal to minus 1/2. Cosine is negative in quadrants 2 and 3, so let's just say quadrant 2 and quadrant 3. And then let's think about the reference angle. Cosine is equal to 1/2 when x is pi over 3. So in quadrant 2, x is going to be pi minus pi over 3. I have a whole video on reference angles if you need to review that. And this gives us 2 pi over 3. And then in our third quadrant, x is going to be pi plus pi over 3. So this is 4 pi over 3. Let me go ahead and highlight these because those are our critical values. Our second step is to draw our number line, and we're going to place our critical values on the number line. We have 2 pi over 3, and then we have 4 pi over 3. And we are going to be looking at the value of f prime. So let's highlight this and highlight that That's the f prime that we're going to be looking at. Let's also add to our number line that our interval is between 0 and 2 pi. What we have to do now is find a value for x in this interval, and this interval. For our leftmost interval, I am going to choose the easiest value I can think of, and that is x is equal to pi over 2. So f prime at pi over 2 is 1 plus 2 times cosine pi over 2. Cosine pi over 2 is 0, so we just get a value of 1. And that is greater than 0, so I'm going to come up here to our graph and put a plus. Now let's pick a point between 2 pi over 3 and 4 pi over 3. I think the easiest value is pi. Now we're going to compute f prime at pi. This is 1 plus 2 cosine of pi. Cosine of pi is -1, so this is 1 minus 2, which is -1. That is less than 0, so we'll put a negative in our middle region. Now let's pick a point in our rightmost region. Let's see, I think the best point to pick is going to be 3 pi over 2. So f prime at 3 pi over 2 is going to be 1 plus 2 times cosine 3 pi over 2. Cosine of 3 pi over 2 is 0, which is really nice. So this is 1, and it's greater than 0. So we're going to put a plus. Let's now draw some lines. Our function is increasing, decreasing, and increasing. So that is going to tell us that we are going to have a local max at x is 2 pi over 3. We need to find the value of the maximum, so we have to compute f at 2 pi over 3. Now we have to be really careful. We are now looking at our value of f of x. So let me go up here and highlight that in pink, because that's what we're going to be calculating. So we have 2 pi over 3 plus 2 times sine 2 pi over 3. This is 2 pi over 3 plus 2. Now we have to think. Sine of 2 pi over 3 is going to be positive because it's in the second quadrant. Sine of pi over 3 is root 3 over 2. So that means that's the same value for 2 pi over 3. So we're going to put down root 3 over 2. And this is then 2 pi over 3 plus root 3. And if we put that in our calculator, it is approximately 3.83. And we'll just label this as local max. Now let's find our local minimum value. That is going to be when x is 4 pi over 3. And this is going to be really similar to 2 pi over 3. We just have 4 pi over 3 plus 2 times sine 4 pi over 3. This is 4 pi over 3 plus 2. And now sine in the third quadrant is negative. So we're going to have a minus root 3 over 2. So f is equal to 4 pi over 3 minus root 3. You put this into your calculator. This is approximately 2.46. So we have a local min equal to approximately 2.46 at x is equal to 4 pi over 3. Let me go ahead and highlight local max and local min, and then let's go back up and let's look at our graph. Our critical points were 2 pi over 3 and 4 pi over 3. That is at this point and at this point. And we can see that we have a local max at 2 pi over 3 and a local min at 4 pi over 3. Let's now look at our third example. I wanted to do this problem because it has something in it that is not in the first two problems that we just looked at. We're going to start just like we did with our first two problems by taking the derivative. F prime of x is going to be 1/3 x to the minus 2/3 minus a minus 2/3 times x to the minus 2/3 minus 1. Let's now rewrite this so it's going to be a little bit easier to work with. Let's write the first term as 1/3x to the 2/3. And then our second term is a plus 2, all divided by 3x to the 5/3. Now let's go ahead and let's get a common denominator. That is going to be 3x to the 5/3. We need to multiply this term by x to make it x to the 5/3. So we have to multiply by an x up on top. So this is just x plus 2 in our numerator. Let's go ahead and highlight this because this is our derivative. To find the critical values, we are going to look at where the derivative is equal to 0 to start. So we're going to set x plus 2 is equal to 0. This gives us that x is equal to minus 2. I'm going to highlight that because that is a critical value. Now we are going to look to see where the denominator is equal to 0, because that can also be a critical value. So we're going to have 3x to the 5/3, set that equal to 0. So that gives us x is equal to 0. Now, we can't just assume that this is a critical value. We have to be really careful, and we have to go back up to our original function and see if it is defined at x is equal to 0. Because of the term x to the minus 2/3, our function is not defined at 0. So x is equal to 0 is not a critical value. It is always good, though, in our next step, step 2, to include this point on our number line because it can be a point where our function changes from increasing to decreasing or vice versa, although we know that we are not going to have a local max or min at that point. Let's go ahead and let's draw our number line. I'm going to put the point x is -2, and then I'm going to draw a dotted line at x is equal to 0, just to remind us that our function isn't defined at that point. Now what we have to do is pick a value in each of these three regions and see what f prime is equal to. I'm going to highlight f prime in yellow because we know then to go back up and look at the yellow function to find our value. There's a lot of points that we could pick for x is less than -2. I'm just going to pick x is equal to -3. So we're going to find f prime at -3. Looking back up to our formula in yellow, we have a -3 plus 2, all divided by 3 times -3 to the 5/3. Our numerator is negative, and then our denominator is negative. So this is going to be positive greater than 0. So let's put a plus up here in that region. Now let's pick a point between -2 and 0. Let's pick -1. So we have a -1 plus 2, all divided by 3 times -1 to the 5/3. The numerator is positive, and then the denominator is negative. So this is negative, less than 0. Put a negative there. And then we have to check one more point. Let's check over here on the right, f prime at 1. This is going to be a 1 plus 2, all divided by 3 times 1 to the 5/3. And we can see that that is all positive. So let's put a plus up here on our graph. Let's go ahead and now draw some lines, increasing, decreasing, increasing. So this means for step 3, we can see that we're going to have a local max at -2. So let's find our function at -2. Now we are going back to the pink highlighted function up above, and we're going to substitute in -2. This gives us minus 2 to the 1/3 minus a minus 2 to the minus 2/3. This is pretty involved. Hang with me. This is minus 2 to the 1/3 minus 1, all divided by minus 2 to the 2/3. Now we can get a common denominator of minus 2 to the 2/3. This gives us this term multiplied by minus 2 to the 2/3. So that's really nice. This just gives us a minus 2, and then we have a minus 1. So we have a minus 3, and then we can say minus 2 squared is 4. So we have a minus 3 over 4 to the 1/3. And if you put that in your calculator, it is approximately minus 1.89, and this is our local max. Before we end, let's go back up and look at our graph. I already put in that we have a critical point right here. That is at x is equal to minus 2, and we found that we have a local max there. You can also see from this graph that our function is undefined at x is equal to 0, just like we calculated. We're now going to be learning about inflection points and the concavity test and walk through some examples. Concavity describes the curvature of a function's graph. If a graph is concave up, it curves upward like a cup. That kind of rhymes. Maybe that will help you remember it. When a graph is concave up, it starts out decreasing and then it increases. So that means that its derivative is changing from negative to positive, and that means that the derivative is increasing, which then means that the second derivative is positive. That's going to be really important when we look at the concavity test. When a graph is concave down, it curves downward like a frown. That also rhymes and it might help. When a graph is concave down, it changes from increasing to decreasing. So the derivative is positive and then it becomes negative. So the derivative is decreasing, and that means that the second derivative is negative. The concavity test is used to find where a function is concave up or concave down. With the concavity test, you have to look at the second derivative. If the second derivative is positive, then the function is concave up. And if the second derivative is negative, then the function is concave down. Another thing connected with concavity is inflection points. An inflection point, like the two down here on our graph that I'm just highlighting, is a point on the graph of a function where the concavity changes. An inflection point can be where a graph changes from concave up to concave down, or from concave down to concave up. Let's now walk through some examples. We are going to find the intervals of concavity, and then we're going to find the inflection points for our function f of x. Just to make things easier, I have written down 4 steps that we can follow, and we'll go through these as we walk through our example. For our first example, we have the function f of x is equal to x to the 4th minus 4x cubed. Our first step is going to be to find f double prime, set it equal to 0, and solve for x. F prime of x is 4x cubed minus 12x squared, and then f double prime of x is 12x squared minus 24x. We are going to set that equal to 0, and we're going to solve for x. Looks like we can pull out a 12x, so we're left with x minus 2. And this gives us that x is equal to 0 and x is equal to 2. Now let's look up at our second step. We are going to find the value of f double prime to the left and right of each of these values of x. So I think the easiest thing to do is to go ahead and draw a number line. Here's our number line. We're going to put an x there, and we're going to put in the points x is 0 and x is 2. And we're going to be looking at the value of f double prime. So let me highlight f double prime, and that is this value right here. Because f double prime is a polynomial in this region and in this region to the left and right of our critical points, we can just look at the leading term to find the value of f double prime. It is an x squared, so it is positive. So we can say it's positive here and it's positive here. Now all we have to do is pick a point in the middle. I think the easiest point to choose would be that x is equal to 1. So we're going to find f double prime at 1. Looking back up to our formula in yellow, this is 12 minus 24. That is less than 0. Doesn't matter the value. We just need to know if it's positive or negative. And let's put a minus right here. Now let's look back up at our steps and look at step 3. We want to write down the intervals for concave up. That is when the second derivative is positive, or concave down when the second derivative is negative. I think it's easiest if we put a little graph on the number line that we've made. If we have a positive, it's concave up, and then we have concave down, and then we have concave up. Now it's really easy to write our intervals. So for step 3, it is going to be concave up on the intervals from minus infinity to 0 and from 2 to infinity. And then it's going to be concave down on the interval from 0 to 2. And let's go ahead and let's highlight those answers. There's our concave up, and there's our concave down. Now let's go back up and look at step 4. We want to write down the inflection points, and those are just the points where the concavity changes. The concavity changes at 0 and at 2. So this means we need to find the value of our function. Let me go ahead and highlight this in orange at the points 0 and 2. So let's write down number 4. We are going to calculate f at 0. That's just 0, so that's nice. And then f at 2, that is going to be 2 to the 4th minus 4 times 2 cubed. This is 16 minus 4 times 8. So this is 16 minus 32, and that's minus 16. So we can say for f of 0, we have an inflection point equal to 0, 0. And we'll highlight that. And then for x is equal to 2, we have an inflection point equal to 2 minus 16. And we'll highlight that. Before we go on to the next problem, let's look back up here at our graph. We found that we have inflection points at 0 and at 2. Those are those points right there. And then our concavity changes to the left and right of those points. We have concave up in this region, and then we have concave down, and then we have concave up again. Let's now look at our second example. I wanted to do a trig one for this example. We are given the function f of x is equal to cosine x, and we are given the region from 0 to 2 pi. Our first step is to find the second derivative. F prime of x is the derivative of cosine, which is minus sine x, And then f double prime of x is the derivative of minus sign, which is minus cosine x, and we're going to set that equal to 0. Between 0 and 2 pi, cosine is going to be equal to 0 when x is pi over 2 and when x is 3 pi over 2. These points then are possible inflection points. In step 2, let's draw a number line, and we'll put these points on it. We have pi over 2, we have 3 pi over 2, and then we are going between 0 and 2 pi. We now want to find the value of minus cosine x in all three of those regions. In our first region, between 0 and pi over 2, cosine is positive, so that means minus cosine is negative, so we'll put a negative here. Between pi over 2 and 3 pi over 2, cosine is negative, so minus cosine is going to be positive. And then between 3 pi over 2 and 2 pi, cosine is positive, so minus cosine is negative. So we're going to have concave down, and then concave up, and then concave down. Step 3, we just have to write down our regions of concavity. So we can say that it is concave down on the region from 0 to pi over 2 and from 3 pi over 2 to 2 pi. And then it is concave up on the region from pi over 2 to 3 pi over 2. Now let's think about inflection points. Because the concavity changes at this point and this point, those are our inflection points. So we have to go back up to our original function, cosine x, and find the value of cosine at those 2 points. So we have f at pi over 2 is cosine pi over 2, which is just 0. So we have an inflection point equal to pi over 2, comma 0. Let's highlight that before we forget it. And then we do the same thing for x is 3 pi over 2. We have f at 3 pi over 2 is cosine 3 pi over 2. That is also 0. So we have an inflection point equal to 3 pi over 2, comma 0. Now let's go back up to our graph and highlight our inflection points. We have an inflection point at pi over 2 and at 3 pi over 2. And you can see on the graph that our function is indeed concave down in this region and this region, and then it's concave up in the region in between. Let's now look at the second derivative test and walk through some examples. The second derivative test is used to find where a function has a local maximum or a local minimum. This may seem familiar to you. The first derivative test is also used to find where a function has a local maximum or a local minimum. These two tests give us the same result. So what's the difference? The second derivative test is easier to use when the critical numbers are close together. Because remember with the first derivative test, you have to pick a point in between each region and test if it's positive or negative. With the second derivative test, you don't have to do that. You just have to find the value of the function at a point where the second derivative is equal to 0. Let's go through all this. The second derivative test tells us that if f prime at c is equal to 0, let's look down here in our graph. Here's c, and we have a derivative equal to 0 because we have a horizontal tangent. Now we have an and f double prime is greater than 0. So it's greater than 0 at C and to the left and right of C. So it is concave up, and that means that we have a local min at x is equal to C. Same thing happens for concave down. If our derivative is equal to 0, that's this point right here, and our second derivative is less than 0, it's less than 0 at C, to the left and to the right, then our function is concave down, and we have a local max at x is equal to C. Let's now walk through some examples. In these examples, we are going to use the second derivative test to find the local maximum and minimum values of f of x. I've written down some steps that we can follow. The first step is to find the critical numbers, and then the second step is to find f double prime, and then check if f double prime is positive or negative at our critical numbers. And then step 3 is we just calculate the local max and mins. Let's see how this works. The first function that we're given is a polynomial, and it's f of x is equal to x cubed minus 6x squared plus 5. Our first step is to find our critical numbers, so we're going to take the derivative. F prime of x is 3x squared minus 12x. We are going to set this equal to 0. We can factor out a 3x, and we're left with x minus 4. So this gives us that x is equal to 0 and x is equal to 4. Now, in step 2, we are going to find the second derivative. That second derivative is going to be based off of our first derivative, so we're going to differentiate that. So we're going to have a 6x minus 12. Now, we don't set this equal to 0. Instead, we take our critical numbers, that's this number, and we substitute it in for x. So f double prime at 0 is minus 12, and that is less than 0. So that tells us that we are going to have a local max at x is equal to 0. Remember, it's just opposite. If it's less than 0, you have a max. If it's greater than 0, you have a min. Now let's find f double prime at 4. This is 6 times 4, so this is 24 minus 12. That is greater than 0. The value doesn't matter. We're just checking if it's positive or negative. If it's greater than 0, that tells us that we're going to have a local min at x is equal to 4. Now, in step 3, we actually have to find out what the minimum and maximum values are. So we need to go back up to our original function and plug in those x values. We have f at 0. That one's easy. That's just equal to 5. So that tells us that we have a local max equal to 5. And that, of course, is at x is equal to 0. Now let's plug in 4. This is going to be a little bit more work. F at 4 is 4 cubed minus 6 times 4 squared plus 5. Let's see. This is 4 cubed is 64 minus 6 times 16 plus 5. So let's see, 64 minus 96 plus 5, that is actually minus 27. So that tells us we have a local min equal to minus 27, and that occurs where x is equal to 4. Let's now look at our second example. This one has trigonometry in it. We're given the function f of x is equal to x plus 2 sine x, and we're told that our interval is from 0 to 2 pi. Let's start by taking the derivative. F prime at x is equal to 1 plus 2 cosine x. Now we need to set this equal to 0 and find our critical values. This gives us cosine x is minus 1/2. Let's see. Cosine is going to be negative in quadrants 2 and 3. In quadrant 1, when cosine is 1/2, x is pi over 3. So using reference angles in quadrant 2, x is pi minus pi over 3, which is 2 pi over 3. And then in quadrant 3, x is going to be pi plus pi over 3. So that is 4 pi over 3. And let's go ahead and let's highlight these because these are our critical values. In our second step, we are going to take the second derivative. So we have f double prime of x. I'm looking right up here to take the derivative. The derivative is going to be minus 2 sine x. Now what we have to do is we have to find the value of f double prime at those critical values. So we have to calculate f double prime of 2 pi over 3. This is minus 2 sine 2 pi over 3. 2 pi over 3 is in the second quadrant. Sine is positive in the second quadrant. So this is going to be less than 0. And this means that we are going to have a local max at 2 pi over 3. Now let's find f double prime at 4 pi over 3. This is equal to minus 2 sine 4 pi over 3. Sine is negative in the third quadrant, so we have a negative times a negative, so this is going to be a positive, so we'll mark it as greater than 0. And this tells us that we have a local min at x is equal to 4 pi over 3. Hang with me. What we have to do now is find the value of the local max and min. So we have to go back up to our original function and see what that function is equal to at 2 pi over 3 and 4 pi over 3. Let's first calculate f at 2 pi over 3. This is 2 pi over 3 plus 2 sine 2 pi over 3. This is 2 pi over 3 plus 2 sine of 2 pi over 3 is root 3 over 2. So we get 2 pi over 3 plus root 3. This is approximately 3.83 if you put it in your calculator. We can highlight this then as our local max. Let's go ahead and highlight all of this in green. There's our exact value, our approximate value, and it's a local max. Now let's do the same thing for f at 4 pi over 3. Looking back up to the top in pink, we have 4 pi over 3 plus 2 sine 4 pi over 3. This is 4 pi over 3 plus 2 sine of 4 pi over 3 is negative because it's in the third quadrant. And we have a minus root 3 over 2. So this is 4 pi over 3 minus root 3. Putting that into your calculator, you get approximately 2.46. And this is a local min. And that's it. You've learned how to use the first and second derivatives to analyze the shape of a graph, determine where a function is increasing or decreasing, identify local maximum and minimum values, and locate inflection points. To really master these concepts, make sure to work through plenty of practice problems on your own.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.